That brings me to the effectiveness of buffer, what is called as buffer range and buffer capacity. Realize that an effective buffer neutralizes small to moderate amounts of the added acid or base, and we saw that in the math problems in the last 2-3 slides. And so realize that if you add too much, then the buffer can be destroyed. So the question is, what are the factors that influence the effectiveness of a buffer? When would a buffer be useful in a sense? And so one can say that the relative amounts of the acid and the conjugate base that you have, and the absolute concentrations of the acid and conjugate base, both of those are important. That means how much of the acid and the base is present in relation to each other, what is the ratio for that, and also how concentrated those are. So in terms of what a buffer capacity would measure, it would basically measure the amount of acid or base that the solution would be able to absorb without a significant change in the pH. And again, it depends on how many moles of the weak acid or the weak base or its conjugate version, the conjugate base or the acid, are present. Higher concentrations would mean that the buffer capacity is going to be higher. Greater is the volume, then too one can say that the buffer capacity is higher. So again, the relative amounts of the weak acid with the conjugate base as well as the absolute values, both of those are going to define the capacity of a buffer. That means how much of the added acid or base can it effectively neutralize. And so one can determine sort of like a range that the buffer is going to work in. So that's what this next section is going to focus on. Now, I think I said that in class as well, that a buffer is most effective when the concentration of the weak acid and the conjugate base, so the acid and the base, when those are equal, that is when the buffer is most effective. So an effective buffer basically means that the resistance will be higher. It will resist pH change. Okay. I want to kind of explore this idea by considering the behavior of some, generic buffer which contains some weak acid, maybe HA, and its conjugate base A minus, for which you have a pKa of maybe 5, and I want to keep the sodium hydroxide which is added to this buffer system. I want to keep that pretty low, similar to what we had done in the previous case. 0.01 is a good number. Moles of sodium hydroxide will be added. But what I want to change is that in one case you have 0.20 moles of the acid and the conjugate base. However, in the other case, I want to change the amount of the conjugate base. So essentially, I want to vary the acid to base ratio in the two solutions. That's what I want to do. So we are going to probe two situations. We are going to add sodium hydroxide, and I'm going to add 0.01 moles of sodium hydroxide to both of those solutions. Both of the solutions contain HA. Both of the solutions also contain the conjugate base A minus. Okay, and in the first one you have equal amounts of the acid and the conjugate base. So you can perhaps envision that you have 0.1 moles of the acid and 0.1 moles of the base. So together they are summing up to 0.2 moles total of both the acid and the base. In the other case, I have a skewed ratio, so I have maybe 0.18 moles of the acid and 0.02 moles of the base. It still adds up to 0.2, but the ratio is skewed. It's not equal concentration. And I want to basically see how it's going to change the overall effectiveness of the buffer. Of course, realize that the added OH minus is going to react with HA, which is the acid component, to give you water and A minus. And if somebody asks you to what extent would this reaction take place, you would say you only have 0.01 of the hydroxide, and so after the reaction has taken place, after the neutralization has occurred, since you originally had 0.1, what's going to remain is going to be 0.1 minus 0.01, and what's going to become of the A minus, since you started with 0.1, and you're going to end up with 0.1 plus 0.01. And the pH and pKa are linked together using what is called as Henderson-Hasselbalch equation, or HH equation, according to which pH is equal to pKa plus log of base over acid, and we'll discuss the details in a little bit, but for now consider this equation as is. And if I have to determine the pH of this solution, I would say that the pKa is 5, which was given to me. Base is 0.11, acid is 0.09, and when you work out the value, it comes out to be 5.09. So if you consider the pH of this buffer, essentially you went from 5 to 5.09. That's not a lot of change. So in terms of the change in pH, one would be able to say that they basically went from 5.09 to 5.00 divided by 5.00 times 100, and that comes out to be 1.8%. Now, if you do the same thing for this other buffer that we discussed, exactly the same thing is going to happen. Your added hydroxide is still going to react with the HA, giving you water and A minus, but realize that you started with 0.18 of the HA, and so the added hydroxide is going to take away a little bit of that. So 0.18 minus 0.01 will give you 0.17, while you're going to add to the A minus, giving you 0.03 as your overall anion. And so now if you had to use the Henderson-Hasselbalch again, you're going to get base over the acid, and when you plug in the numbers, 0.03 for the base, 0.17 for the acid, it comes out to be 4.25. And now if you look at the percentage change in the pH, it went from 4.25 from 4.05 to 4.25, and if you try to figure out the percent, it comes out to be 5%. So realize that the buffer with equal amounts is more resistant to the pH and is an effective buffer. So we basically proved the principle that resistance to pH change is a more effective buffer, and so a buffer becomes less effective as the difference in the relative amounts of the acid and the conjugate base increases. So just as a guideline, you can perhaps keep this in mind, that an effective buffer must have a base to acid or a conjugate base to acid ratio in the range of 0.1 to 10, so plus minus 1 on a logarithm scale. So for a buffer to be reasonably effective, relative concentrations of the acid and the base should not differ by more than a factor of 10. You can keep that in mind as you define the buffer capacity and the buffer range for a given buffer. Okay, let's talk about the Henderson-Hasselbalch equation in a little bit more detail than what we have seen. So Henderson-Hasselbalch equation, sometimes also referred to as the HH equation, is an equation that enables me to find the pH of a buffer solution in a more simplified manner by basically deriving an equation for the equilibrium for the weak acid. So recall, my weak acid HA is interacting with water to give you hydronium plus A minus. This is aqueous. Charges are always aqueous, by the way. Water is the only one that's liquid. And we can write down for such a situation that Ka is equal to hydronium times A minus over HA. Okay. All you got to do is rearrange this. So you can perhaps write down multiplying both sides of the equation. So BS again, both sides. Multiply both sides by HA. And you would be able to write Ka times HA is equal to hydronium times A minus, and I'm going to divide both sides by A minus. That would give you Ka times HA divided by A minus is equal to hydronium. Okay, and now we are going to take the negative log of both sides. Negative log of both sides. So that means negative log of Ka minus log of HA over A minus is negative log of hydronium. But what is negative log of hydronium? Aha, that's pH. That's pH. What is negative log of Ka? That's pKa. And you can write this right now, it's acid over base, but that's with the negative sign. If you want to make that negative sign positive, then you will have to make the denominator numerator, numerator denominator. So this equation will boil down to pH is equal to pKa plus log of base over acid. That's how we got that. So it's nothing fancy, it's just basically a simplification of the Ka and a mathematical operation on that. Now if you make sure that the x is small and the approximation holds true, then you can consider that the equilibrium concentrations of the acid and the conjugate base are going to be identical to the initial concentrations. And so to determine the hydronium for any buffer, you can multiply the Ka by the ratio of the concentration of the acid to the base, and you would be able to determine the hydronium ion concentration from there. What I mean by that is that if you have a solution that is 0.100 molar acetic acid and you have mixed that with 0.100 molar sodium acetate, then since you know that hydronium is going to be equal to Ka acetic acid over acetate. And so both of these concentrations are 0.1. This is 0.100. That too is 0.100. So one can say that the hydronium ion concentration is going to be equal to Ka in this case scenario. And this was a case scenario where both the acid and the base were exactly equal. What would happen if these were in a ratio, you know, maybe 1:10? That is when, in terms of the Henderson Hasselbalch, which is pH is equal to pKa plus log of base over acid. So if these were in the ratio 1:10, then you can perhaps envision that you would be reducing the pKa by 1 unit to be able to get the pH. Alternatively, if they were in the ratio 10:1, then you will be increasing the pKa by 1 unit to be able to get the pH for that solution, which is why we say that it's plus minus the buffer capacity essentially, or the range in which the buffer works the best is perfect if it is within plus minus 1 unit for that buffer. Now we did a buffer earlier. We studied CH3COOH, CH3COO minus, where both of these were 0.1 molar, and we had determined mathematically using the ICE method, we had determined the pH to be 4.78, I think was the pH. I want to see if we can apply the Henderson-Hasselbalch to determine the pH of this buffer. So pH is equal to pKa plus log of base over acid. Of course, I will need the pKa of acetic acid, or at least the Ka of acetic acid, which by the way is 1.8 times 10 to the negative fifth. So I can say it's negative log of 1.8 times 10 to the negative fifth plus log of the base here is acetate, so that's 0.1. The acid here is acetic acid, which is 0.1 as well. 0.1. Both of those are going to cancel off, so that's not going to actually count. That's going to be log of 1 is basically 0. So all you got to do is get the log of 1.8 times 10 to the fifth, and that should give you your overall answer. So on my calculator, I am determining minus. So on my calculator, I plugged in the value, and I'm getting 5 minus 0.255. That comes out to be 4.75. So notice ballpark they're about the same value for Henderson Hasselbalch and the equilibrium method. And I think the difference is because then we used 1.78 or 1.7 as against 1.8. So let me try that one more time with 1.7. 1.7. 2.3 minus 5. Yep, and it does come out to be 4.77 if this is 1.7. Okay. All right. The question is, I want to prepare a buffer solution with a pH of 7 and one with a pH of 9. Which of the following pairs of weak acid conjugate base should I use? So if you want pH of 7, you obviously do not want these pHs. You would want to keep the pKa within the plus minus 1 range. So the first one can be made using the last choice, and if you wanted a pH of 9, then you should stick to the 9.25. So as long as you keep again the plus minus 1 for the range of the buffer, you should be fine. All right. The question is, using the HH equation to calculate the pH of a buffer solution prepared by mixing equal volumes of 0.2 molar bicarbonate and 0.1 molar sodium carbonates. Okay, A value is provided to you. You know the HH equation is pH equals to pKa plus log of base over acid. So you have to decide for yourself which part is the base, which part is the acid. So again, go back to chapter 15. The acid would contain the proton. As simple as that. Negative log of 5.6 times 10 to the negative 11 plus log of 0.1 divided by 0.2, which is going to now give you your overall answer. So just plug in the numbers, and when you plug in the values, this part comes out to be 10.25, and log of 0.1 over 0.2 is nothing but half, so that comes out to be negative 0.3010. And when you plug in all the numbers, your final answer comes out to be 9.95 as the overall pH for the solution. Alright, the question now is, give a recipe for preparing sodium bicarbonate and sodium carbonate buffer solution that has a pH of 10.40. Now, we just saw that for bicarbonate carbonate system, the pKa was 10.25. In the last question, I calculated that. So, we are going to use the Henderson Hasselbalch equation again, plus log of base over acid. This is 10.40, this is 10.25, so you can say that 10.40 minus 10.25 is equal to log of base over acid, which is 0.15 is log of base over acid. And so hopefully you can envision that e to the power of 0.15 is going to give you the ratio in which these must be present. So the base over acid ratio should be, since it's log to the base 10, it's 10 to the power of 0.15, which comes out to be 1.412. So if you can keep the ratio of the bicarbonate and the carbonate, or rather the other way around, carbonate to the bicarbonate, if that ratio can be maintained to 1.42, you would use that to prepare this buffer. So realize, in terms of moles, it really depends on how many liters, like what's the volume that you're seeking. In this case, they did not ask anything, but if you had to make, let's say, 1 liter, then if you're beginning with 1.412 molar solution of carbonate, that would mean that it should be just 1 molar with respect to the bicarbonate. And so if that ratio is maintained, you would have the specific pHs for that system. So just to summarize, what did we learn? We learned about the buffer range. The lowest pH for the effective buffer would be if the pH is pKa minus 1. The highest, that will be the lowest. The highest will be when it is pH is pKa plus 1. So it has to range between plus minus 1 unit, and the effective range for the buffering system is going to be over a ratio of 10 between the conjugate base and the weak acid ratio. So what that means is that if your weak acid has a pKa of 5, then the buffer will have a range of 4 to 6. Remember that. And depending on your system, for instance, if somebody asks you which acid would you choose to combine with sodium salt to make a pH at of, let's say, 4.25 is what you need. And there are several choices that are given to you, just the similar example that you saw in the previous slide. Then you are going to select one which is within the plus minus one, for that, and you are going to make your selection based off of that.